Good. So last time, I mean, we talked about conditional probability, which is a very important one actually, because that says that if something happens, then given that you know this information, now what is the probability? And one thing that was important and interesting is that this we had these things that A and B might be independent, but then they conditioned on C, it might be not independent, or vice versa. That's interesting. And this is the issue that, I mean, as I mentioned, consider this event just a set of a subset of outcomes, essentially. And in that case, you will see that, I mean, when you somehow intuitively, when you consider these events, these are just some subset of outcomes. So in that sense, when you condition on C, it means that some of these outcomes are not there anymore because you know that one of these things happens. So in that case, it means that now after when you condition on C, the word will change essentially because there will be a remaining subset for A and B. And that can be, I mean, there is not much relation between this and the original ones. And that's the idea essentially here. Good. And now we will go to the Bayes rule, which is very important. And again, we are teaching about the game theory. As we discussed, we mentioned about the motivation in the first sessions. Why do we care about it? And lots of important aspects of game theory in the chocolate, or also known in this class, carrot game. But we need to really, I mean, understand the formula, and everything is math. Like game theory without probability, we cannot do anything. Another thing which is very related also is linear programming that we will discuss as well. That's another tool that we will talk next session. And then we will go to game theory. This is the way that I put it, such that you know everything about the class, and then we will, and about the background. These are all crash courses, of course. You should take the courses. You don't lose anything if you learn more about probability stuff or take other courses. And this is one of the things that, for example, in the top companies, like for example, Facebook or Google or something like this, you may actually get interviews from probability, and it can be quite heavy probability stuff. So if you improve your background in probability theory, work hard and do also some exercise like interview questions, etc., that actually you get lots of benefit of it. It means that in your paycheck. Good. Okay, the Bayes rule is one of those things. Again, there are several interview questions that they make turns into the Bayes rules essentially. And generally, these are like some of the slides that I have put it. I mean, some students or some people that they wanted to apply always said, okay, actually take a look at these slides again before going for interview, because that says essentially the things that you needed for interviews. You may need something more, but at least you should know all of this. Good. What is the Bayes rule? The Bayes rule essentially says that if we have two events A and B, just if you have two events A and B, and so assume that the probability of A is greater than 0. We don't, okay, yeah, actually here I assume probability of B greater. Sorry. Yeah, if probability B is greater than 0, then, and thanks, this is important to mention this. When you see something, please say something. So we cannot say the probability of A condition on B that we just discussed. The probability of AB means A intersection B. AB always means A intersection B over probability of B. Then this is equal to, I mean, then I will just write the probability of B is the same. Now I will essentially expand based on the probability of A here. And that would be the probability of B conditioned on A times probability of A. Just the same formula I have, because this can be A on B conditional B or B conditional on A. So I will just use the other one and do that. So what does this do? This is a very interesting thing, because here, why do we make essentially things complicated? It's not actually complicated. The catch is that sometimes you want to get the probability of A conditioned on B, But you don't have enough information to do that. However, you have probability of A, you have probability of B, and you have probability of B conditioned on A. And we will give an example essentially. Sometimes this is much easier. So this something like probability of A or probability of B is called probability before any evidence. This is a prior probability. Then this is likelihood. This is assuming A, how likely is the evidence? Or like this is like generally called likelihood, probability of B over A, that we have it from some other experiments or some other knowledge. Then we want to get the posterior. The posterior is important. This is the conditional probability after knowing the evidence. So that's essentially, we are mentioned likelihood is that assuming A, how likely is the evidence, and then it's that what is the actual conditional probability after seeing the evidence. And this is called inference, deriving some unknown probability from known probability. And this is one of the most important, as I mentioned. This is one that you may get essentially a Facebook interview that they are asking this essentially. And you know, this job market becomes tighter, so you need to be actually super ready for that. And this is very important. These kind of conditional probabilities or Bayes rule actually are very important for A/B testing again. And I mentioned A/B testing. I just mentioned it again that I mean there are some traffic. So for example, that happens a lot in this kind of companies, big tech, that you have a new website, you have a new thing, you want to see that comparing this versus previous one, whether this is better or not. And then you need to consider lots of biases. One of the issues for the biases is that, for example, if you just use the people who are, for example, you create this new website, you want to see whether the people like it or not. One important thing is that the people should not have a bias. What's the meaning of that? So if this is my Chase Bank, and then they change it tomorrow to something new, I use it, I don't know, for 10 years, 5 years or something like that. I hate this new one anyhow. Because I knew everything before. Now I don't know where are these things, so I don't like it. So the way to do that, essentially, you should not do it with the old customer. You should do it with the new customers. Those people, they don't have any bias. So that is one important thing, for example, in the A/B testing, the people are using it a lot. So you should just consider old one, old website, new website, but with new users or very relatively new users, such that they don't have any bias toward the previous. The other thing is also this one. So lots of this probability that you want to compute essentially in the, there are two things. It is called frequentist method or Bayesian method. And the Bayesian method, you may get more information. This is the whole idea of inference. You may get more information with the past experience that you have done. Generally, these are more complicated, but if you can get something interesting, it would be saving a lot of money, because these things, like consider Amazon or Google, etc. When you do such kind of thing, you need to send enough traffic. And this enough traffic means that if this website just, sucks, essentially, you lose millions of dollars. Even in, say, generally between 2 to 4 weeks experiment that you are. So you should be very careful if you can get some information without running the website or getting, with less traffic, then you should do that. So that's the idea, that this type of things actually makes money in practice. You see, 1 million is a lot of money. You can hire 3 people, like 4 people essentially for a year. And so if you can save something, that would be great. If you can write some math and you compute something, that would be great. Anyhow, so here we are inferencing essential probability of A condition B from the probability of B condition on A. And you can see lots of questions. Just say Bayes rule in Facebook interview questions, you will find some of them actually. And that's a good example that you can go through that. This is about game theory. I don't want to go through this one, but that is, I think, on you to go and check it. Good. Let's see this example. This is a very nice one. That again, this is this type of question that I have mentioned, like in the interview or something, is very similar to this one. This is a bit more game in it, but they are very similar to this. So, say there is a bag, and there are 2 envelopes. So one has a red ball worth $100 and a black ball. Another one has two black balls and the black ball worth nothing. So consider sand versus gem. And you randomly grabbed an envelope because you don't know what is inside, and then randomly took one of the balls out. It is black. The question is that at this point, you are given the option to switch them. Should you switch or not? So again, so here again, you have this bag, it's a black bag. There are two envelopes there. They have two balls there, each of them. And then you will go there, take one of this envelope out, and then take one of them at random. There is a black. And again, the situation is this one that I have mentioned here. One has two blacks, one has one black, one red. And then the main question here is that whether you should switch or not. Okay, so we want to see whether we should switch or not. And this is the whole concept of inference with Bayes. This is the math you need to write. Okay, let's define E as the envelope that we have. So, so it can be one as like RB, red and black, and or two like BB, black. So let's B be the event of drawing a black ball. That's the thing that we know that because this is the event that we care about. Now, here, I mean, what is the probability of E condition non-B? By the way, here E doesn't mean really. Really, the thing is that E equal to 1 or equal to 2, because E can have two choices. But in general, I mean, either this is when we don't write it, it means that it's as a general, that E is equal to 1 or equal to 2. That would be essentially probability of B conditioned on E times probability of E over probability of B. And this is the one that we care essentially. Why? Because the probability that we really care about is probability of E equal to 1 condition on that we have a black ball that we draw. Correct? This is the one that we care essentially. Probability of E equal to 1. Probability of event E equal to 1. Conditioned on the fact that essentially the one that we have it is like the first one, because we care about the one that has one red. So the probability of the envelope that we are taking, this envelope essentially, because if we know that this from this envelope, like essentially is it the red blue, red black, or black black, then we know that what we should do. So this is the probability that we care. Probability of E equal to 1, or you can say E equal to 2, doesn't matter, as long as we have some ideas about that we should do. But that would be conditioned on, then we can just reverse it, then say that what would, and this is the interesting part. So this is if this is something like black is coming out, what is the probability that is the first envelope or second envelope? Then we will turn it into the other one. What is the probability that essentially if E equal to 1 or equal to 2, a black is coming out? Then that is much easier to know because we know this one in advance. We don't need to run this thing to know essentially. And then the probability of E and probability of B are simple. So let's just write the math. So we want to compute probability of E equal to 1 where condition on B versus probability of E equal to 2 condition. So what is the probability of B condition that E equal to 1? It would be 0.5, correct? If E equal to 1, what is the chance that you are bringing as randomly a black one? Would be half. What about for the second one? If it is second one, the probability is 1. Now, what about the probability of E equal to 1 or probability of E equal to 2? Because we took one of them at random, both of them are half. That we need. Now, what is the probability of B? Probability of B really doesn't matter because we want to compare actually these two and then for comparison, both of them have the probability of being the denominator, but who cares, maybe. But let's do the compute it. What is the probability of B? Probability of B, which is one essential, is that we are bringing just the black one, would be 3/4, because 3 out of, we are essentially doing one random process. Then from this, selecting an envelope, and then from one of these envelopes, we are selecting another one. So you can think the whole thing that I'm from one of these 4 balls, I'm drawing one ball. What is the chance to be black? 3/4. So now we have that. Now we can compute this one. Now, what is the probability of, for example, what is this probability? So that would be probability of B conditioned on E. So here in this case, would be B conditional equal to 1, which is 0.5, times the probability of P of E equal to 1, which is again 0.5, over the probability of B, which is 3/4. So in this case, which is equal to 1/4 over 3/4, which is equal to 1/3. So this is the probability that this one that I take it is actually is a equal to 1. This one, like the one that has essentially the next ball is. Now let's compute the same thing, probability of E equal to 2 conditioned on B. The same thing essentially. So here we are doing, everything is the same here. Probability of E is the same, probability of B is the same. So the only thing, probability of B conditioned at equal to 2, and that would be 1. So here, instead of 1/2 in the second case, let me just change the color. So in that case, conditioned on that, this is 1. And then everything would be the same. So it would be 1, it would be 2/4 here, and then it would be 2/3. So it means that the probability of E equal to 1 conditioned on B is 1/3. Probability of E equal to 2 conditioned on B is 2/3. So it means that in this case, the probability that we got a good envelope, it would be less than the probability that we have the bad envelope. So that means that you should switch to the other one and take the other one. Again, of course, this is, everything is probability. You might be dead wrong, and you cannot, come and blame me on that. Everything is probability. This is like, you cannot say that, yeah, you may do it and then you lose it. But this is the probability. In expectation that we will talk next, actually, this might be beneficial. Good. Great. So let's go there and talk about the. So Bayes rule actually can be more complicated. Suppose that, we have events B1, B2 to Bk that form a partition of this. Partition means, this is exactly the definition of partition, is an important one. They don't share any essentially outcome. At the same time, the union of them would be S. Good. Now, assume that the probability of Bi is greater than 0 and probability of A is greater than 0 in this case. Generally, if you want to condition both of them, you need to do it both greater than 0. That's a safe thing. Then you can say probability of Bi conditioned on A is equal to probability of A conditioned on Bi times probability of B and over probability of A. And again, you need both of these conditions here because of, you are using both of them here and here for both. Good. So we have, let me just. That is something should have not happened. I don't know why it's not finding some Zoom things. It is strange, but let me draw. See. Oh, Maybe that is the problem. We need to first change the draw. This is exactly the bugs that you can have it in the software. Good. Okay. So we have this partition conditions, these two conditions, and then we are just writing this, and we need this one for here, and we need this one for here. So we just write it down. Now let's go and see what else we can say. Yeah.
What is probability of B on U to be greater than 0?
I mean, because if you want to write, just to be safe side, you may actually relax that. But generally, if you want to write, because we are using the reverse of that here, but you may not need actually that condition. Okay. But to be in the safe side. These are some corner cases that it is always good to check in the programs and do that. But here, I'm assuming that to just be in the safe side. Okay, so in that case, I can just write this one. So probability of BI conditioned on A is equal to this one that I have written it already. Now, let's write this one. So here, probability of A, because B partitions on that, so whenever, we can say that essentially this is equal to probability of A conditioned on S essentially. Because one of these events should happen. The outcome should be in one of the BIs. So that's the reason that we can write this formula and sum it up over all cases. So this is the probability of A. We can say the probability of A is equal to probability of A intersection with one of these BJs essentially, because one of these events should happen. One of these outcomes happens, and that happens in one of these guys. So this essentially is equality. You can write it more formally. I think that would be a good exercise to say why, if we have this thing, then we can write it like this. But that's the intuition. Good. Let's continue. Now let's expand this one again. AB, let's do it this term, write it in terms of conditional probability. Good. So in that case, as you see, then we have the probability of A condition on BI. This is just a numerator that doesn't change anything. The numerator, we have changed it. And then instead of that one, we are just writing this one. Just say probability of BJ times probability of A condition on BJ. Good. I think, you were right. That really is not needed to have this one, because this is just, we are not dividing it, actually, because we are not assuming this one also here, that BJ is greater. So here in this case, so this is actually a nice formula. So whenever you have you can partition the events into some events, B1, B2, to BJ. If you want to get the condition probability of BI conditioned on A, how come you can do that? You can just, this is a very nice formula. The denominator says that, okay, probability of A conditioned on BI times probability of BI. And then the denominator says sum over all possibilities of this type of things. Because this is, you see, this form is exactly the same form here. It says that BI conditioned on probability of A on times conditional probability of A conditioned on BI, which is the same formula here. So this is a very nice formula, actually. It's a very symmetric one. Say that if you want to have such events, you have partitioning of these events, then if you want to condition the probability of BI, if you want to get the probability of BI conditioned on A, you can always compute this one for BI and then sum it up over all things for the denominator. That's a nice formula. Again, this is some formula that can be used if there are 3 events, for example, that BI is involved, can come in, say, in an interview or something, or in the real world, essentially. Because this interview question, generally, they are trying to mimic the real world that you need to solve these problems. Good. Having said that, so this is a bit more complicated version. Let's go to the third thing that we want to talk about random variables and probability distribution. That's, again, super important, especially for game theory course that we have it here. Probability distribution, joint probability distribution, etc. And we talk in particular about expectation and variance. I mean, expectation generally is more important than variance, but both of them are essentially important, and we will talk about. First, a random variable. So, what is a random? So, a random variable x is just a numerical outcome of a random experiment. It can be between 0 and 1, it can be between any range. So, this is a random variable, it's randomly ordered. And you can actually do this one in, for example, Python. You can easily generate this type of thing. You can make it integer, or you can make it real. Everything you can just generate essentially random. Or you can do it at C. Good. So, and these are like, okay, this is a pseudo-random generator, etc., because it's not really random, but almost it is random for all practical purposes. So, what is the distribution? The distribution we talk a lot in this class, game theory, is a random variable. The distribution of a random variable essentially is a collection of possible outcomes and the probability of those. So you can essentially write it down. Especially, we will talk more about a discrete case. Discrete case is good. I mean, what is the probability of x is equal to x? I mean, we will just, for example, mention it by this one. So you can write it. So this is essentially x equal to 1. This is the probability. So then x equal to 2. Then this is the probability, and so on and so forth. For all possibilities, here you will say the probability. This is essentially some kind of, you will say the probability. This is everything that you can describe a distribution. Of course, one way to do it is that through a vector. So you can have a vector, an array, and say this is essentially, this is the x equal to 1, the first one x equal to 2, second one x equal to n, and this is the probability that we are. In the continuous case, I mean, you cannot just, if you say that probability of x equal to x is always 0. So you need to take essentially some interval. And in this case, then we need to take the integrations. Integration means sum in this area. So essentially, if you have something between a and b, and this is the curve, this is the area. So you need to sum it up essentially. Yeah.
What does theta mean in the subgroup?
What? Theta is the name of the distribution.
Ah, okay, that's.
So this is, I will say that a distribution theta.
Okay.
I mean, we may drop it essentially if it is known from the context. Okay. Now, so this is the definition, and this is very important. And it is important that we are showing that using a vector. Because it is important that this is a one-dimensional vector for one variable. Then if we have two variables, x and y, then a joint distribution of them is again the same thing. There's a collection possible of outcomes along with the joint probability. And joint probability is the same thing that we have seen it. This is essentially what is the case, that this is essentially intersection. This happens and this happens. So it would be probability of x is equal to x and y equal to y. How come, or how can we essentially represent this one in a nice format? Would be a two-dimensional vector. So this is for x. Essentially, this is equal to, so here it is x is equal to x, and this is, so this is x is equal to x, and this is y is equal to y. So then you will come here, and this is the one that describes this. So we are showing that. And this is very important because when we consider, and it can be three-dimensional. This is for 2. It can be x, y, z. Then it is three-dimensional. That's exactly the way that later we will discuss it when we have two players, like the one that we have seen it in the carrot game, that x and y. And then in that case, I mean, there are two players, and then we are discussing about this probability as I do take this action, the other one would be taking the other actions, and so on and so forth. So that we see exactly this one in the future, essentially, this course. And we will represent this one with this one. What is the main property of this? The main property of this vector is that sum of the numbers, sum of all the numbers is equal to 1. Because this is a probability distribution. Over all events, we should have the probability of 1. That was one of the axioms of it. The same thing here. This another interesting thing. Here, the probability over, again, the sum over matrix is 1. The sum over the whole matrix is 1. Not on, it is not the case that in each row is 1, no. Or each column is 1. The sum over whole matrix is 1. Again, very important property that we have. So essentially, two important probability. So in this case, you can say one thing that we have it, all numbers also are greater than all numbers. These are not necessarily, integer, but the numbers are greater or equal to 0, the same thing here. Because we don't have negative things in the probability. So that's the only condition. This is a vector that the sum is 1, and all of them are greater or equal to 0. The same thing here is a matrix. The sum of the whole matrix is 1. And then each of them is greater than or equal to 0. So that's a joint distribution that we talk a lot about it. And finally, when we talk about the support of a distribution, generally we talk about a discrete distribution, because for concrete, as I mentioned, doesn't mean that what is the probability at this point. Is the set of all x for which probability of x is equal to x is greater than 0. So all of them which are essentially mixed, are important, essentially. Good. So let me clear everything and then go for the next one. Good. So, let's, see this one. Let S be the set of all sequence of 3 rolls of dice. And so S is essentially a set of all sequences that you can have. So this is S is essentially all outcomes that we can. X be the sum of the numbers of the dots on the 3 rows. So what are the possible values for X? Yeah. Through 18, because it can be 1, 1, 1 through 18. And then in this case, you can say that, for example, the probability of X is equal to 3. Well, this should be 1, this should be 1, this should be 1. So it would be, and each of them are independent. So it would be 1 over 6 times 1 over 6 times 1 over 6, which is 1 over 2 over 1 over 6. What about the probability of X is equal to 18?
2 over 216.
Again, 1 over 16, because 18 happens if this is 6, this is 6, and this is 6, right? There is no difference between this is 1, this is 1, this is 6.
I was thinking of X.
Yeah, so So this is X equal to, I didn't mention it here, but this is X equal to 18. So this one is again the same as this. So this is some kind of symmetry you will see. Now, what about a probability of X is equal to 5? So let's see how come we can have that. So X is equal to 5 if we have something like this. If we have 1, 1, 3, correct?
Yes.
That's one case. But this can be also, we can have it 3, 1, 1. Or we can have it 1, 3, 1. And all of them is this 1 over 2 over 16. There can be some other case as well. 2 to 1. And again, 1, 2, 2. And then 2, 1, 2.
think that's all.
Is there any possibilities else to get it 5?
There are. If you could choose some total possibilities, so it's going to be. Wait, no, correct.
6 over 60.
Yeah, 6.
Good. It is again important that this one, I mean, you need to write a math. That's exactly the thing that they need you from these questions. I mean, they will ask, and of course in the future, because note that if you don't compute such kind, I mean, this is not maybe not dice, but similar things essentially, and they have seen this in some big tech essentially, like Amazon more actually, that the people are talking, and I mean, this thing that they are mentioning, they don't know the basic math, and if you don't know the basic math, you try to run an experiment. And then if you don't do it, then you get a wrong implication. That gives you a wrong implication. So it means that you should change the website. How you should not change the website, essentially. And that can be actually, or I mean, maybe at the end of the day, they understand, because if they lose money, then they at the end they say, okay, I lost money. Something got done wrong here. So we can get it. But sometimes it's not easy, because there were several events happen at the same time. You don't know you lost the money from which event, essentially. So that might be even catching the bug is not that easy as well. Good. So let's go to the next things. So this is this one. Now the next one that we talk about is expectation, which is again very important one. Good. Let's talk about expectation. So a random variable x, which has a probability of, so random variable x out of this essentially means that this is the probability distribution. Then in this case, the expectation of this is essentially x times probability of x is equal to x. So in some sense, you can consider it, this one as the weighted average. Like, of course, average would be just x. Weighted average means that we have the probability, which might be different. So in the empirical sample, it means that the case that all of these x1, x2, and xn have the same probability, then all of them would be xi over 1 over n here. But this 1 over n, you can just factor out, and then you will bring it here. But that in a empirical sample, it means that all of them have the same input. But it might be not the case always. For the continuous case, again, we need to use the integration. We say that x, essentially, p of x, d of x. We talk less of that, essentially. But in game theory, in general, we are using this, essentially. There are several cases that you need to actually write the integration. And as I mentioned, expectation is essentially just a weighted average, essentially. What are the weights? The weights are probability. The most important things in the fact about expectation is linearity of expectation. So it means that if there are two events, x1 and x2, then probability of x1 plus x2 is equal to two variables, x1 and x2. It's the probability of x1. It is the expectation of x1 plus expectation of x2. That is equal to expectation of x1 plus x2. And again, I mean, that you can see it. Why is it the case? I mean, you can just write the formula. Again, it is this is not a magic that I bring it. I just, everything, like, you can just prove it using this. Good. So let me clear everything. Let's go and see the example again. This one, we don't have the answer for this one. You can think about it. So here, this is a problem. The same experiment that we had it, S be set of all sequence of 3 rows of dice, X be the sum of the numbers of the dots on 3 rows. What is E of X? So let me, so we are resuming recording. Yeah. So for the first one, as I just discussed, so this we can just use the, essentially use the, here in some sense, you need to define 3 variables. Instead of X, I will define it X1, X2, and X3. And each of them essentially, x1 is that what is the expected number for the first one, first dice. Second dice. So then I have it. Then I know that x is equal to x1. See, everything is math. I will write it x as x1 plus x2 plus x3. So in that case, then E of x is equal to E of essentially x1 plus x2 plus x3. That now I'm using linearity of expectation. So if you want to actually write a formula or write some of the things, it would be good if you do it even for assignment. Here you will say 1. You may write it 1 on the top of it. And then say 1 because, and in LaTeX you can do that. You can write actually something on top of something and say 1 because of linearity of expectation. What about this one? For example, if we call this one 0, 0 is because of the definition. So everything that we write, it should have some justification. We cannot just. And this is the right way of writing, essentially, in a paper or any formal things, such that people can do it and they can check it. So here, the probability of E of x is equal to sum of these numbers because of the way that I defined x1, x2. Now, this one would be equal to E of x1 plus E of x2 plus E of x3. Now, so this essentially is, this is linearity of expectation. Finally, I wanted to write, this is a lemma that I define. So what is this lemma? I'm saying that how you can write this one as a formal thing. And this might be a bit simpler here, but not always that simple. If you want to write it formally, actually takes effort. So you may have a lemma. And what does this lemma? Says that E of x1 is equal to E of x2 is equal to E of x3. And we call it lemma 1. Why?
Because it's the same, if they're the same dice.
Because these are the same dice. So otherwise it could be different. So essentially this is the proof that we will write it is that because the same dice. You can write it a bit nicer than this. Or you can give it to ChatGPT to make it nice. Because it's the same dice. That's the reason. Now, here I can say that this one is equal to 3 times E of x1. Why? I will say here lemma 1. Because of lemma 1. Now you can compute. You may have a lemma 2 that you will compute there. Then I don't say a lemma 2. You said that E of x1 is equal to what?
3.5.
It is 3.5. Why? Because you need to sum 3 plus 4 plus 5 plus 1 plus 2 plus, 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, it would be 3.5. Why? Because you can also do it like 1 and 6 would be 7, then 2 and 5 would be 7, so the average would be 3.5. So that would be, again, this one, which is equal to 7.5. This is by lemma. So this is the way that I have written it to just show that how you can write a formal proof. So he mentioned, okay, so 7.5, but to write it in a formal way, that's the way that you need to.
You like me 10.5? 3 times
7.5.
Yes.
Yeah. You see, even that you are not careful, you may do a mistake essentially in the computation. Always good to check your multiplication with Google.
Yeah.
It would be 10.5 essentially. Yeah.
I think 21 by 2.
Good. So this is the way to write in a formal way. And this is like if you write a paper or a report anywhere, that's the way that you need to write. Again, even I didn't write the whole math here, whole right wording, but I think you got the idea of how we can. Now, if you want to do this one, essentially, if you want to say, what about the product of them? We don't have any product of essentially like linearity of product. Yes?
Because they're independent, couldn't we just multiply them?
No, I mean, there's nothing, I mean, like that. You may, I mean, you need to write the formula. So the independence means that, I mean, essentially the probabilities are, yeah, you can just multiply these two probabilities. But anyhow, this is the formal way that you need to write it down. And I don't want to say yes or no. I mean, you need to do that. One way, actually, you can just think about it. I mean, how can you do it smarter? Maybe there are some cases that you can actually say, like you may use lots of symmetry that exists here. And this is actually one of, I believe, one of the exercises that you have it even in the homeworks or similar things that you have it. This is a good thing to think about it. See how can you do it efficiently. But you cannot just use linearity.
Yeah, I think you can multiply probabilities that are independent of each other, but you can't multiply because values are
exactly. I mean, everything should come from math. Everything is math we are talking about. Good. So this one essentially as an exercise you can do that. This the first one we solved it, but not the second. Yeah. Or reader. Or listener, or I don't know, watcher. Great. So good. But again, this is super important. Don't assume something in the probability. Probability is a non-trivial thing. Even the very advanced people make mistakes essentially. And I mentioned this was the example that I have mentioned that thesis at MIT essentially that had the issues of didn't consider exactly this consider of it was not clear that I mean he considered independence how a little bit of correlation exists. That a little bit of correlation can essentially change the whole thing. Again, also watch this video that I had it with Professor Aravind Srinivasan. He's a professor here. This is a live one that we have it together. That's very good. If you want to get, he has a great essentially knowledge about the probability and randomized algorithm. Just watch that one. You will get something that you may not read in the books essentially, or may need to read a lot of books to get it. I mean, there are some parts that we talk about negative correlation, positive correlation, etc., which are beautiful actually. And you can get very good ideas about this. So in some sense, the probability, one of the main things essentially is that probability is some things. Then we have independence versus non-independence, which means essentially not independence means correlate. And then all this, and the conditional probability. And this variance. So we have this concept essentially, variance. So what is, I mean, maybe a better parameter. So variance, we will say V. There is another parameter, this one, which is called a standard deviation. Standard deviation, sigma. And the sigma is equal to actually a square root of V. Why do we care about this one? This is like a very natural thing if you consider as a sigma. So sigma, it says essentially what is the yeah, so this is essentially the square root of V. But let's actually go and talk about the variance. Then we will talk about this one. So variance of X, you said that what is the expected value of X minus E of X to the 2. Good. So you want to, and this is essentially a good measure. You want to say in terms of like the, for example, the distance in general. But you want to see that if this variable that you have it, how much is concentrated? Because this is the concept that we, I think, we talk more about it, about the being a risk averse versus risk prone. So you don't, yes, I know that the expectation is this number, but how much we can deviate from that. That's essentially the concept of variance. And it's compute what is the expectation of X minus E of X to the 2. Good. What is the expectation of X minus E of X to the 2? And sigma is just essentially the square root of variance. So in some sense, sigma, you can think about it, roughly speaking, sigma says, what is the expectation of x minus e of x? It's not quite that, but that essentially captures this. That like this x variable, how much deviates from e of x? That's somehow the thing, because you take it's not exactly like that, this is the exact formula, but this is somehow the intuition for standard deviations. What is the expectation of? So here we are computing variance of x is expectation of x minus e of x to the 2. So one important thing, again, that people are missing, expectation of, what is the expectation of a constant number? A constant, the same constant number. That's very important. E of x, another important thing related to this, e of x is a constant number. E of x is not a random variable. E of x is not a random variable, is a constant number. So we just compute this one. Say that e of x to the, so this is, you just expand it, x to the 2 plus e of x to the 2 minus 2x e of x. Good. Now, again, expectation of, we are using linearity of expectation here. So this is the linearity of expectation, which is, it is equal to, I mean, e of x to the 2 plus e of x to the 2 minus 2 times e of x times e of x. And here, note that, again, I'm using, so for example, for this one, what is the expectation of e of x to the 2? Because this is a constant, it comes completely out of it. So it will be e of x to the 2, not e of x, because it will be the same as e of x to the 2. The same thing here. When I multiply these two, so what is the expectation of this part? The expectation of this part is that 2 is a constant number. E of x is a constant number. So they will come out of it, would be 2 times e of x. The only thing that remains would be e of x. And now, of course, then we have this one. We have e of x to the 2 plus e of x to the 2. So this, and this would be minus 2 times e of x to the 2. So this cancel out would be e of x to the 2 minus x. So that's the formula essentially for that. I mean, talking essentially, variance is important, but generally, I mean, for concentration bound, we are using variance. A bit maybe less in this class considered to expectation. Expectation, we are talking a lot in this class. And generally, some parameter which is easier to work on it. Again, expectation said what is the expectation. Variance said what is the risk, essentially. How much we are deviating from this expectation. Because it might be a crazy thing that, yes, one time, I mean, that some... so the variable can be all over the place, and just expectation may not give the full information. Variance gives a bit more information. So these are, I mean, some distributions that we are talking, and these are important. I'm going quickly over them. So first one is the Bernoulli distribution. So Bernoulli distribution essentially is the case that the outcome of an experiment can either be a success or failure, 1 or 0. And the probability of x is equal to 1 is p, probability of x equal to 0 is 1 minus p. And then you can write the formula like this, but essentially this is the same formula as this. What is the expectation of x is easy. I mean, x is equal to 1 is equal to, so it would be 1 times p plus 0 times 1 minus p, which would be essentially p. Variance of x is e of x to the 2 minus e of x to the 2. Note that e of x to the, so e of x to the 2 does not change anything, correct? Because x to the 2, if it is 0, x to the 2 would be 0. If 1, it would be 1. So it does not change anything. So in that case, e of x to the 2 and e of x are the same. So in that case, would be just p. What about e of x to the 2? E of x is p to the 2, would be p to the 2. So here we are using the fact that e of x to the 2 is indeed equal to e of, because x to the 2 is equal to x. Is 0 to the 0 to the 2 would be 0. 1 to the 1 would be 1. So that will be the variables. So this is a Bernoulli distribution that we talk. Now let's go to the next one. Yeah. So the next one, of course, would be binomial distributions. So here, this is the random variable x stand for the number of. So we have n draws of a Bernoulli distribution. Essentially, a biased coin maybe. With probability p it becomes 1 or head, and this probability 1 minus p becomes 0. It's a biased coin. And then you are n draw of this one, and you want to see how many times we have essentially head. That's essentially the thing. This is the formula for that. And again, now, why do we have E of x is equal to n times p?
Because there's n Bernoulli trials.
N Bernoulli. So here we are using linearity of expectation. Good. So we have the linearity of expectation. Now, one important thing here is that what about the variance? If you remember, variance of Bernoulli was p minus p to the 2, which was p times 1 minus p. Correct? Here we have n times that. In that we don't have linearity of variance in general. But here we have it, it seems. Interestingly, I want to go maybe from the Bernoulli distribution, I will go. So this Bernoulli and binomial, both of them actually, they are, so here actually we have the linearity of variance. So here we have a linearity of variance. In this particular case, not all the time. Why do we have that? So the reason that we have it is because of this. I will come back to this. So because both of these cases, these are the normal or Gaussian distribution. Generally, what is the shape of a normal Gaussian distribution? These are very symmetric ones, essentially. They are coming here and coming there. They might be heavy tail or, I mean, essentially not heavy tail. Generally, a normal Gaussian, this is very natural type of distribution, very symmetric. They have their, what is the thing that they have it? We know that, I mean, we decide about them. There are two parameters for this one that decide exactly what would be the shape of this. One is the mu, the expectation. The other one is sigma to 2 or variance. If we know that, we can draw exactly this diagram. And this is the formula. One important thing here is that if we have the first one and the second one, x1 and x2, both of them are coming from a normal distribution or Gaussian variance, then if we consider x is equal to x1 plus x2, then actually they would be another Gaussian with the of course, the expectation would be sum of the expectation. That is general for everything. But then we have here we have the linearity of variance as well. You can also sum it up their variance. So binomial distributions, for example, R or Poisson that we will talk, these are all normal or Gaussian. And again, two important parameters. I can draw this curve given that the sum of the probability is 1. I always use that. And you give me essentially mu and the variance or standard deviation. Then I can draw this thing and I say what is that. This is the exact formula that comes out of it. It's a bit complicated, but you can always uniquely essentially draw this. And now let's go to the one more one that I wanted to talk about it. You see, I mean, this is for binomial distribution. If you see that all of them have this kind of Gaussian things. Again, these are some kinds of a special case of this kind of things that they have mentioned. So Poisson distribution. Poisson is another one. It is called memoryless distribution. Like the thing that has happened essentially happened. We don't remember anything in the past. That's a very important thing about the Poisson distribution. So for Poisson, that is interesting. The E of x, the expectation of x, and the variance of x are both lambda. So I can just, you give me this essentially lambda, I can define the whole things. You can, they are coming from binomial distribution. You can consider that I'm fixing the lambda equal to be NP. So I will say that my my mean or essentially expectation should be lambda, and then but the number of the number of trials can go to infinity. So in that case, and this is the exact formula for that. So this is the way that you can consider it. So there is the variance of x is also lambda. You can actually write it down to compute it. But this is exactly the probability. So this is, we always write this type of things to say that this is what is this distribution theta, and what are the probability for if x is greater than or equal to 0 is this formula, and otherwise would be 0. What would be the shape of it? So the shape of this would be essentially this. For you see, always we are starting from 0 essentially here. So always we are starting from 0, and then this is the shape that you can have it according to the whether the lambda becomes. So as you see, I mean, when it is lambda is very close to 1, it is very, I mean, concentrated, and this one it becomes more relaxed. But all of them are essentially at the same time. These are also normal distributions with different lambda. So this normal one is very important, and you should know that. And lots of things in the nature actually is a normal. That's the thing that they call it normal or Gaussian essentially. We talked about some of them, but essentially the fact that all of these experiments that we are talking, all of them are normal is important. And for normal distributions, we have the linearity of variance, which is important. Otherwise, we don't have linearity of variance. Great. So I think here everything that we wanted to say. This is a crash course on probability. You can read a lot about it, but I think it's a good one. Again, for interview, I will say take a look at this one and try to remember the things that you had in. Next time we will talk about another very important to linear programming or convex programming for game theory. And then we have the tools now. We will start and we will talk about it. And these are, again, I already mentioned some ideas about game theory. Why do we care this? But we care more about this. If there is no question, essentially, I will just pause.